morphisms, etc., etc. I'm not going to get into that. We don't have time for any sophistication, and neither am I capable of any sophistication, so it really doesn't apply. But it's basically a two-category. So I'll just give you a list of properties and how we can apply them to our needs. So what's a two-category in general? Well, it is the same as a category in the sense that it has objects always denoted by dots with A, morphisms denoted by arrows as usual, F between A and B. But now the new ingredient is that we also have two morphisms. And what are these? These are maps between morphisms. So visually, given two objects A and B with two different morphisms between them, with the same source and target, these two, then if there exists for all these pairs some map from F to G, which I'll call alpha, alpha goes from F to G, so that again, you know, alpha will have a source and a target map, so the source of alpha will be is equal to F, and the target of alpha is equal to G, and nothing. So these things will be called the two morphisms. I'll indicate them with these double arrows, just to remind us that they are not the morphisms. And what do we need? We need to have an identity for every function. Need an identity two morphism. One F for all F's, for all F morphisms, which is exactly what you expect. So it basically maps F to F, and we will draw it, we will write it as a 1 with a little f. Remember before we wrote the identity as an object 1 with a little a, now we'll call it 1 with a little f to mean it sends f to f. And then we will need to be able to compose these guys, these two morphisms, just like we did with morphisms. So basically it's as if we were doing all the game we played before with the category. Now, again, where now our objects have become the previous morphisms, and we're now applying the rules that we want for morphisms to the two morphisms. So we need these things to be composable. So you can see already there's different ways of doing this, right? So I will say compositions because there's two. There's one is the vertical, and they are called like this because they look vertical when I draw them. So if I have an F prime, sorry, I have to draw this bigger. So if I have two objects, A and B, and then I have an F going from A to B, but also an F prime going from A to B, and also an F double prime going from A to B, I can have a morphism, a two morphism from F to F prime, and one from F prime to F double prime, and I will call this composition AD. Note that all these have the same source and target, and this composition will be called A prime after, and I draw it with a little star because I don't know to distinguish it from the other composition we'll have, so I write it A prime star A, which maps from F all the way down to F double prime, so it goes from F to F double prime. But there's also something else I can do, and that is a horizontal composition. And this one, again, it will look horizontal when we draw it, that's why it's called that. And here we will have different source and target maps for the different morphisms we're interested in. So we start with an A, a B, and a C. We have an F and an F prime that go between A and B, and we can have a G and a G prime between B and C. And here we can have an alpha prime, and here we can have an alpha. And we will say that this is equal to, this is a definition again, to G after F getting mapped to G prime after F prime with what we will call alpha prime horizontal composition with alpha. So notice that now we are going from A to C, right? We have combined these two things here, let's say, horizontally. And yeah, so A horizontal composition, alpha prime, so a horizontal composition with alpha will go from G up F to G prime F prime. So, okay, so it's clear that these two are two different ways of composing, right? Once we're composing two things with the same source and target, and now we're composing two things that only share one object in common. And I want all these compositions to be associative as always. Compositions have to be associative, both vertical and horizontal. And I also need them to be compatible, right? And I will show you in a second what this means, and I will go, I think, to the next slide, because this is the key point, and when you see this, you will start to say, ah. So, why I went to all this trouble. Compatibility of these compositions means that the diagram I'm now very uglily drawing has to be well defined. And let's say I have F, again F prime, F double prime, G, G prime, G double prime, alpha, alpha prime, beta, beta prime. Well, this has to be equal. On the one hand, I could first combine beta with alpha and beta prime with alpha prime, right? So I could say GF, map down beta horizontal compose alpha, and then beta prime horizontal compose alpha prime. Notice we're now going from A to C all the way down to G double prime F double prime. To reduce this further, I have to now cut out the middleman, and I can do that by vertically composing. I have F after G, A, C, F double prime, G double prime. The reason I wrote this arrow very far over here is because inside here we will now have, let's see, beta after alpha, vertically composed, sorry, wrong way around, beta prime alpha prime vertically composed with beta after alpha. Okay, so far, right, I've only done the stuff I've told you I'm allowed to do.
You didn't mean to switch the F prime, F and G.
Sorry, no, I didn't mean that, obviously. And also my F's and my G's look awfully similar, right? This is also not so good. So, G, F, with a little dot. But so far so good, right? We're allowed to do that. But what we're also allowed to do is, instead of starting with this horizontal composition, I could start with the vertical one, right? So I could do beta prime vertical after beta, down from G to G double prime, and I could compose vertically alpha prime with alpha, taking F down to F double prime, right? And again, I can reduce this further by now doing the horizontal composition. From A to C now, G after F, G double prime after F double prime. And how do we write this thing inside here? Well, B prime star beta, horizontal compose with alpha prime star alpha. I'll write it out again nicely, a little bit below maybe. But you start to see, compare these two, they have to be the same, right? Otherwise this diagram would be ill-defined. If how I combine these with each other is different, I mean, that would be a very weird situation. So it's reasonable to require these things to be the same. And what this, rewritten out nicely, what is this saying? B prime after alpha, beta after alpha, sorry, b prime after alpha prime, b prime after alpha has to be equal to b prime vertical composed beta, horizontal composed with alpha prime after alpha. And what do you start noticing? Aha, these two guys have been switched, but they have not been switched so strictly. I mean, we're not saying that whatever alpha and beta are now, they all have to live in some sort of abelian structure, right? Because we have very different products happening between them. I'm not saying I know right now what they, according to the category, to whatever two category we're dealing with, they will be whatever they will be, but they will not necessarily be the same. So you see that, starting to see where I'm going, again, painfully obvious, painfully predictable, but you can see that basically we have defined, I mean, what as mathematicians do, we have defined our problems away, let's say. We have created something where the problems we had don't exist because we've just said these things don't have this problem. Definition. Now, of course, it's a matter of, for us to fit our problem into this language so as to guarantee that it is actually one of the examples of one of these structures. So this thing here is called the interchange law, and it is basically the crux of the matter here. And this is the big novelty, and this is what we're going to make use of. Of course, let me just quickly say we also have two functors. I'm rushing this a bit, but in the notes it will be more in detail. But two functors, again, they will map, I will just draw it now. They will map objects to objects. They will map morphisms to morphisms between the same objects, obviously, you know, and so on. And of course, they will have to map two morphisms to two morphisms, and they will have to preserving both products, the star product and the horizontal product, so the vertical and the horizontal. Meaning, so for instance, f of f star, sorry, alpha, f of alpha star alpha prime has to be, of course, equal to f of alpha star f of alpha prime, and the same with the horizontal composition, right? So basically, again, same as before, a functor is a map between two categories, between two categories, right? Preserving everything it can preserve, and the identities. Of course, of course, the two morphisms have to have an identity, and f of the identity at f has to be equal to the identity at the f. Right? So preserve everything it can, and so on. So already you're seeing where I'm going with this. So I've defined something that doesn't have, that has this nice interchange law that already starts to look like that awful drawing I made at the beginning, you know. And I have also got this functor, so maybe I just do exactly the same thing I did with gauge theory, where I would just make a two-functor between whom? Well, we'll see that. Let's get to that now. So I have examples of these two categories. So take our previous path group, so let's take our smooth manifold, smooth M, with its points and its paths, and will now include surfaces between paths. So gamma prime, some sort of sigma, well, actually I should now use the proper notation. Call this a double arrow, so let's say I call this sigma. The sigma 2 morphism takes gamma into gamma prime. Of course, there exists an identity, just leaving gamma where it is. I can compose these surfaces. Of course, I can compose surfaces on a smooth manifold. I can compose them vertically and horizontally. And they have inverses. And again, for the composition to be well-defined and associative, I'm going to have to restrict to thin homotopy classes of these surfaces, and they have to be lazy. You know, I mean, I'm not going to get into it, but you can read all about it in in these notes by that I refer to in my own written notes of Baez and Huerta. So you can verify that this all is somehow well defined, what I'm saying. But anyway, we've basically got our first, we've got what we need more or less. We've got our paths, and we've got our, let's say, two morphisms. Sigmas will be our two morphisms. And I will also quickly show you how to compose things, because going back to that drawing of that worksheet of a string that I drew, where I started to argue about this little box down here. Let's see how we can get this in this language. So say we start with a path, or the composition of two paths from here, from this point here to this point here, apply a two-morphism, bam, send it up, let's say, for instance, to this path. So, okay, there is also something I didn't mention. I can combine two morphisms with morphisms, of course. I can take a, let's say, gamma 1, gamma 2, with some sigma in the middle, and I can easily compose this with, let's say, a gamma 3, which is just a morphism, because I have an identity to morphism, so I can just, with this identity at gamma 3, take this down to gamma 3 again. So what have I got? I've got gamma 1, gamma 2 composed, mapping with sigma, horizontal composed identity at gamma 3, down to, whoops, this new path, gamma 2, gamma 3. Sorry, this is wrong, this is a 3. Right? Makes sense? So composing, the fact that it's composing surfaces with paths is already defined. We don't need to worry about it, right? So here I start with a little surface that takes that first square up, that first path up to this path, and now I can, this kind of operation here is called, we call it whiskering, because we're like putting, whiskers on a surface. We're putting little, whiskers on the side. So here I put two whiskers. Let's say like this, and already I have set the scene to take another two morphism, and take this guy to here, and another one, say, to take, this path up to this one, right? That's all okay, right? And thanks to this whiskering, I know that basically what's happening here, horizontal composition will go this way, because you can see that I can combine my red arrow horizontally with the blue one, right? Why? Because they share only the one object. They only share this, so they cannot be vertically composed. Obviously, they can only be horizontally composed. But then this structure here that I get can be vertically composed now with the black one, or I could do it differently, or I could start, let's say I could start again with the red, vertically compose it with the black, and then take the whole thing and horizontally compose it, let's say, with the blue. And I can take the other combinations, and I'm going to build, in this way I'm going to build up the whole grid, not just the first, starting from down here, I'm going to build, the whole, go up and cover the whole surface. And the fact that whichever way I decide to do this, whether I first do this and then this and then this, or whether I go from here to here to here, all of these are the same, is guaranteed by the interchange law, right? We agree?
But couldn't you just rotate it? If you rotate it,
you can draw it whatever. I mean, the point, you can draw it whatever way you want. That's the whole point. Is that we're not, whatever. Yeah, if you want to. I mean, if you can figure out. This was my this was the nicest way I found of drawing it, but if you find a better way, you know, draw it whichever way you can. Keep in mind, the important thing is that when you do vertical composition, so this one, this star, the vertical one, it has to, the composition of the vertical ones have to be like this, so they have to have the same source and target, right? So this, they have to have this in common. So here in this drawing, you have to find to vertically compose paths. So you can, you know, it's not so easy to see here. You have this path. Let's say you have this path, right? Is the corner, and you can take this up with a two morphism to this path. Okay. So now, how do you vertically compose? You need another path that goes around here, right? Not so obvious. How are you going to draw it? But I'm sure you can find a way. I mean, with this whiskering and all the compositions you're allowed to do, you'll find a way. That's exactly the point. Is that whichever way you decide to combine paths and surfaces, you can wiggle your way up. Oops, where is it? From here, you can go whichever way you want up here, right? And the result will always be well defined because we have this interchange law that tells us that these compositions have to all be compatible. So, okay, but right now I'm still talking about, you know, joining surfaces and so on, which is something that you can formally do. You just write down, you know, paths as maps from the interval 0, 1 to the manifold, surfaces as 0, 1 squared to the manifold. Formally, you can patch all these things up. But that doesn't yet tell us how to do gauge theory, right? I'm just talking about manifolds now, and okay, what have I said? Nothing. all I've said is that the manifold, together with its smooth path and its smooth surfaces combining paths, is an example of a two category. Again, it's a groupoid example because all of these things are again invertible. So it's again, it can be called it's a groupoid. So, but this is still the easier case. Not so obvious to see is the two group. And the two group, actually, the two group is actually, I'm going to say right now, I'm going to start calling it right now strict two group, because we're going to go to non-strict things later, and I want to make it clear this is a specific example. So the strict two group will be made up of 4 ingredients, and we'll see now how they all come about. So we'll start with a single object, again, G, which we will again denote with this bullet. And now, and again, we have, of course, the morphisms, you know, as before. The morphisms are the elements in G. But we will now also have, so now we want to see what are two morphisms. So I don't know what they are, but let's say we call them H. We call H the two morphisms that have such that the source of H is the identity at the bullet, meaning the identity of G. Since there's only one object and there's these G morphisms between it, there's also an identity from the group to itself, and I will just call it one bullet. That's the symbol I use. So H will make all of these. So that means I have here a G, always indicated by the bullet. I have an identity in G, and with H, I can map this to what? Well, to what we call abstractly the target of H, whatever that is. And by combining two of these, you can immediately see that under horizontal compositions, these are closed, right? Whatever this gives, it'll be a map from one to something, right? Agreed? Oops, sorry. T of H prime. And in here we will have H horizontal combined H prime, which also means that the target of H horizontal composed H prime is equal to T of H times T of H prime. So first we see that horizontal composition makes the H's a closed set, right? And they have inverses, of course. I mean, well, of course. Well, yeah, they do have inverses because you can look at these guys, T of H, are in G, right? They have to be morphisms. They have inverses, so there will be a H inverse corresponding, there will be a, yeah? What already? Jeez. There will be that, and this will be T of H minus 1. Anyway, they make a group under horizontal composition, closed and invertible, etc. They are also, furthermore, T is the map that takes H to G, and it is a group homomorphism, right? So far so good, that's nice. So I have described this, I have given you this H, the T, and now we still have time maybe to look at what alpha is. What is alpha? Well, let's go down a bit, and let's look at this kind of drawing. Last thing that we'll do today. G, identity, G minus 1, and then two morphisms, and we'll take our identity, we'll take it with a H to some T of H. Our G minus 1, we'll take it with the identity of G minus 1 to just itself, and G with the identity at G, we'll take it to G. What is drawn in this diagram is that, let's say that all that stuff in the middle here is basically 1G, horizontal composed with H, horizontal composed with 1 at G minus 1, right? And I will call this the action of G on H, just nomenclature, just notation. But what I can say is that the target of this action of G on H, I can read it off. This is the target, right? So it is G, T of H, G minus 1, meaning that T is G equivariant. So that's already good, right? And we know, so basically we basically now know how G acts. We know how G acts on H. How many seconds? I'm used to thinking in seconds, Can I maybe, what else do I need here to say? Just quickly say one more thing. Let's say when two G's act, right? So I've told you that going from 1 via the action of G on H, we know what that is. We've just said it is kind of an adjoint action of G on H. And now we'll just slam it in between curly G, a new G, a curly G action, with again identities. We'll just slap it in between two things that are the same as what we used before, just to say that the action of G tilde on the action of G on H, reading off the target of this whole thing, is basically equal to the action of G tilde G on H. Convinced? That looks reasonable, right? Because we know you can convince yourself by just putting a T in front of everything, and you know that, also on this side, because you know that the target of this action is G tilde G, T of H, G tilde, oops, I don't remember how to do inverses. Right? And this looks awfully similar to that, right? So you can believe me. And that's how far we'll go. But basically, what is this? What is this basically telling you? Well, nothing. This is if we look at alpha as being a map from G to the automorphisms. I have yet shown you that it's automorphisms of H. You can convince yourself that it's automorphisms of H by checking. Actually, you can do that. What is alpha G on H prime? Exercise. And once you have that, you will see that it is indeed a map from G to the automorphisms of H. And you can also say that it is not only a map, it's a homomorphism, right? Because of this. So G tilde after G just acts in the appropriate way. And so that's why we call it an action, because it is an action, because it is because it's homomorphism to the automorphisms from one group to the other, right? Okay, so that's done. So that's so much for that. Tomorrow and then next time a little bit more, because the point of defining all this is to still get finally arguing that there's a functor between that manifold with the surfaces to this kind of abomination that will give us some information about about two-form connections, and we'll see that the next time. And ignore the notes that Peter sent you before because they were full of errors and typos, so I have corrected some of them, so I will give you a new version right now. Sorry? Well, there's stuff where I just didn't use the right tag, and there's just some bracket valued objects. And I challenge anyone to figure out what I meant by bracket. So, well, it's either G or H, but No, but okay. Actually, there are exercises in the notes, even for this first step up to here, which is not all of what you have, but you can see more or less what you can do. And I would, if you're interested, do draw a few of these diagrams, because once you've drawn a few, you realize how ridiculously easy it is. Because even if it looks kind of scary